we're gonna keep it cruising. We're gonna bring on my man, Yujian. Where you at? Where you at? There he is. Oh, dude. All I can say is people love freaking vector databases, so you are gonna hit this out of the park. It's gonna be too easy. Can you hear me all right?
I can hear you. Can you hear me?
Yep, I hear you loud and clear. So, dude, I'm gonna take it. I'm gonna let you take it from here, and I will be back in another 30 minutes. I want to mention to everyone, if they have not checked out Zilliz, oh no, not messages, solutions tab right here. You've got the virtual booth from Zilliz, and these are the people that bring you Milvus. So you know what it is. All right, I'm going to leave you, and I'll be back in like 20, 25 minutes, man. Looking forward to this chat.
All right. Okay. I think everyone can probably see the screen now. Yeah, so welcome to this talk. My name is Yujian. I'm going to be talking to you about the key to scaling LLM applications. So everybody's kind of building LLMs now, and one of the major things that we are concerned with is how do you scale these applications and how do you productionize these applications, right? Some of the problems with LLMs come with mostly data and cost. So they don't have the domain knowledge that you need. They don't have up-to-date data, right? For example, GPT-3 was trained up until September of 2021. Or it can be incredibly expensive to rerun many, many queries, especially if you're going to be running them frequently. So a little bit about me. My name is Yujian Tang. I'm a developer advocate at Zilliz. These are my contact links, listed below. The QR code will take you to my my LinkedIn. So if you've got your phone out, you can scan that and connect with me and message me. A little bit about Zilliz. Zilliz is the company that is behind Milvus, which is an open source vector database. We are the world's most popular open source vector database, and mainly are really, really good at scale. And I'll tell you about why Milvus has such good performance at scale later on. But for now, that's kind of what you need to know, right? And these are some links to go find us. Either join us on Slack, come talk to us about vector databases, unstructured data, AI agents. We've got channels for all this stuff. And also check us out on GitHub. Milvus is a project that is written in Go. Okay, so the content of this talk is pretty much going to be talking about large language models. I'm going to walk you through neural networks in general, kind of like, starting from not way back, but it's about 10 years ago up until now, talking about some of the challenges that LLMs face, right? The data challenges. Then we're going to talk about the CVP framework, which is a framework that we here at Zilliz abide by and advocate for in terms of building out production level LLM apps. And the CVP framework stands for ChatGPT, vector databases, and prompt as code. Then we'll go over, what is a vector database, because we're going to be talking about them, but we're never really going to cover them until the end. We're going to talk about what is a vector database, and we're going to talk about Milvus. And if at the end we have time, I will go over a quick demo of how you can build a scalable LLM application, or I'll go over a quick demo of a scalable LLM application. So part one, unless you've been living under a rock, you know about ChatGPT, you know about Claude, from Anthropic, about Bard from Google. They've been in the news like crazy, and there's been a ton of development in this space. So let's go back to 10 years ago when convolutional neural networks got pretty big. And the reason we're going to talk about this is because convolutional neural networks give you this thing called local context. So you can see from this kind of, very simple image, Milvus is the world's most popular open source vector blah. And you can see that these arrows are pointing to the neurons that are right next to them. And that is basically what local context is in the sense of a convolution. The next kind of thing that came about was self-attention or global context. I didn't finish the sentence. This one in the slide obviously just says Milvus is the world's, and then it should say most popular open source vector database. But you can see that the way that the self-attention architecture is different is that we are pointing our connections to every neuron in the next layer. And finally, we have causal attention, which is kind of the way that these statistical, stochastic generational models work, right? You have every token after the first one has access to the first one. Every token after the second one has access to the second one. So in this case, Milvus is the world's most popular vector database. The word world has access to Milvus, but Milvus doesn't have access to the word world. And this is directional global context, right? So this brings us to kind of today how LLMs are made. Obviously, LLMs are not this simple looking. They have transformers and encoder decoders, whatever, however you want to kind of imagine that architecture. But at their core, LLMs still are stochastic models. They fit this neural network. The underlying, principle of neural networks is that they are stochastic. And so what happens really is if you are working with an LLM is going to generate the sentence, Milvus is the world's most popular vector. And the way it finishes the sentence is it asks the data, basically, given all of these former tokens, what is the most likely next word? And so in this example, we say that database 0.86 most likely next word. Obviously, the downside to this is hallucination, which is kind of what these slides are kind of focused around, oriented around, is solving the problem of hallucination as one of the examples of vector database usage and why vector databases are such an important part of the LLM stack. So I'm going to just show some math here for those of you who are into the math behind these things, right? So basically, the way that you formulate this problem that LLMs are solving, the way they're getting these statistics, the statistically most likely next token, is that given some set of tokens, T0, T1, all the way to Tn, predict Tn plus 1. And the way that we formulate that in a probability perspective is the probability of database, given that Milvus is the blah, blah. Very similar to Bayesian statistics. If you kind of remember that, you can think of the way that these generative models generate their tokens in the form of these statistical models. So challenges with LLMs, these are very, very popular models, but they still have some of their own issues. And like I was saying earlier, one of the biggest issues is hallucination. And so, for example, if we query ChatGPT, how do I perform a query using Milvus? It's going to give me some code. And the code is actually going to look like it could be right. Because this looks like Python code, right? But what we'll notice if we understand, if we know how Milvus works, so if we've read the documentation, this is an open source software, so the documentation is out there, right? We'll know that this is actually not how you use Milvus. This is not how the connection is done. So later on, we'll see how this is actually done. But for now, I just wanted to show this example of what is a hallucination. So the solution to these hallucinations is basically to inject domain knowledge into large language models. Really to inject domain knowledge on top of them, on top of large language models, but into LLM applications. And how do we do that? We use the CVP framework. So the key idea behind the CVP framework is that we can view LLM apps as a general purpose computer, kind of like how computers work. There's a processor, there's memory, and there's code. And in this CVP framework, you will use ChatGPT or any other LLM. So you could actually replace the letter C with L, but we've just decided to go with C. But this can be interpreted as the CPU, the processor, the main compute power behind these LLM applications. V is the vector database. This is the storage, your ROM, kind of your hard drive, in a sense. And so in this example, like Milvus could be a vector database. And then prompt as code is basically your interface. So like the UI in a sense, the code that makes the UI, the OS, whatever, the way that you interface between the processor and the storage. It's a type of code, right? And an example of an application that uses this CVP framework is an application called OSS Chat, which if you use will actually give you the correct way to use Milvus. In this chat, this is a chat bot that talks to open source software, and we've got a bunch of different open source software on there now. It's not just Milvus. There's like PyTorch, YOLO. There's many other, AutoGPT. There's many other open source softwares that we've put behind OSS Chat. And the way this works is basically we get the documents, we generate some set of embeddings from the documents and the answers. So we'll ask ChatGPT to generate some questions that would make sense based on the documents as well. So you're working with the question space and the answer space. And then we use Zilliz Cloud to host these, to hold these embeddings. And when a user comes and asks a question such as, how do I perform a query using Milvus, they should get a correct response back like this, because we've scraped the actual code, the actual documents that are related to the software. And so we also use this thing called GPT Cache, which was built, which is another open source library. And this was built originally as part of OSS Chat because we saw that there were some questions that were asked many times, and it is ineffective, inefficient, and it's costly to run the same questions multiple times through an LLM when you could actually just say like, hey, maybe many users come and say, how do I use PyTorch to resize my images? If you have 10 users coming and ask that, you probably want to cache that and just query your vector database and say, okay, here it is. Here's your answer. We're just going to return this. We don't need to, query the LLM to recreate the answer for us, or to decompose the query if you're using something like Llama Index. Okay, so how does this solve hallucinations? Why does this work, right? So I've told you that this is supposed to work this way, but why does it work? So what vector databases do is they give us an access to domain knowledge, and then they allow us to perform semantic search on domain knowledge via the vector embeddings. And vector embeddings are these numbers that represent some sort of object. In this example that I've shown here, the object is a word. And this example kind of shows you that if you take the word queen and you subtract the word woman and you add the word man, you get the word king. And this is a very, I hesitate to say old because it's not that old, but like this is a seminal paper in this space, and the advances in technology have gone far beyond what is shown here. This is a very simple example of vector. There's no such, like nobody's operating on two-dimensional vectors anymore. The standard size is like, so if you're using OpenAI, I think it's like 1536. If you're using Cohere, it's like 768. There's some that are like 384. So the standard size of these vectors are hundreds. So in practice, the way this works, the way that you can operate on these vector embeddings, do math on objects like images or words, is you take your knowledge base, you run it through a deep learning model, and then you get the vectors out from that. You get the vector embeddings from your deep learning model. And the way that works is that you actually take the outputs from the second to last layer of your model in order to get the vector embeddings. So a deep learning model will typically do something such as classification, or maybe like entity recognition, part of speech tagging, something like that. And instead of asking the model to give us the classification, we just pull the values from the second to last layer, and that is a representation of the object that we put into the network. And then we put that into a vector database such as Milvus. Okay, so what is a vector database? Why do you need one? Vector database, here at Zilliz, we like to say that a vector database is a database purpose-built to store, index, and query large quantities of vector embeddings. And with Milvus, focus really is on billion scale, right? Is on these large quantities of vector embeddings. So this is a bunch of text dump, but the basic idea that you want to get from this slide is there are actually other solutions to performing vector search or to working with vector embeddings. You don't need a vector database. You can use a high performance vector search library such as Facebook AI semantic search, maybe similarity search, FAISS, or you can use hierarchical navigable small worlds, HNSW. You can use Annoy, which is approximate nearest neighbors, oh yeah, which is built by Spotify. But if you want to, have a more production-ready vector search vector similarity application out of the box, then you probably need a vector database. So vector databases allow you to do things like filtering on your vectors. So if perhaps you want to filter on some of your metadata. It allows you to do hybrid search. So for example, you can search your text and a dense vector, maybe a sparse vector. It provides you with backups, right? Your data is backed up. You're not going to lose it really easily. High availability. You don't have to worry about scaling, maybe sharding if you're doing a lot of streaming data. Aggregation search, parallel search, lifecycle management, multi-tenancy, working on a GPU accelerator. For example, we have a GPU accelerated integration with NVIDIA. And one of the other things we do really well is the billion scale storage. So let's walk through some vector indexes so that you can understand kind of how we're comparing these vectors and how that works. So this is the one I was talking about earlier called Annoy, which is approximate nearest neighbor search. And this builds a binary tree. And the way it does it is you take two separate points in your space, and then you split the space in half, and then you do it again and again and again and again until you have maybe 3 vectors, 4 vectors, 5 vectors. This is a hyperparameter that you can control that is in one section. And this produces, like I said, a tree kind of index. And the way that you search is you say okay, find me, the closest space and then the closest vector in that space. Then there's IVF, which, this looks like a Voronoi diagram. And basically the way this works is some sort of k-means type clustering algorithm. And you come up with, say, some number of centroids. So you throw your data in there and then you cluster all your data, and then you get these areas that are clustered around a certain centroid. And when you search, what you do is you say, let's say I want to search 5 centroids. Maybe your dot is somewhere in here, right? You search these 5 centroids and then you see which one of the actual vectors is closest to your new data point. Then HNSW, this is a really, really popular one. And it's also a somewhat complex algorithm. Basically, you're creating a graph index of all of your data points. And then when you insert them into the graph, what's actually happening is you're also assigning each data point a uniform random variable. And that uniform random variable determines what layer they're going to be in. So for example, let's say, we're building something and we're assigning a uniform random variable. If you get between 0 and 0.9, maybe you're in layer 0. If you get between 0.9 and 0.99, you're in layer 1. If you're between 0.99 and 0.999, you're in layer 2, and so on and so on and so on. So as you can see, the layers get sparser and sparser as you go up. just because of this uniform random variable. Now, that does mean that it's possible that you have 4 million data points and everything is in layer 0, but it's unlikely. And the way the search works is you start at the top layer and then you just sparsely search your way down. And it's really fast because it's graph search, right? Your graph is already built. You just have to find the next point. So let's talk a little bit about, architectures. Why is Milvus fast? Why is Milvus good, right? Milvus uses a distributed system native backend and uses these. So in this diagram, you probably don't need to pay attention to most of this. You just need to know, okay, how do I interact with it? SDK sends it to a load balancer. Load balancer balances all the, the requests. And then the important part is to know the stuff about like the query nodes, the data nodes, and the index nodes. Typically, these nodes can actually be really the same node, right? They're like kind of like a pod in Kubernetes. But we have dedicated nodes that do different things because it makes better performance, basically. So the query nodes they query the database and they return the data that you need. The data nodes hold the data that you need to kind of work with in memory, and the index nodes do your indexing when you're indexing. And I'll just address this here. And with Milvus, you should almost never need to re-index because of the way that the architecture is Milvus actually saves all your data in 512 megabyte chunks instead of one whole, block. And that makes querying much, much faster because then what you do is you query these 512 megabyte chunks in parallel instead of, running through an entire 1, 10, 30, 100 gigabyte block. And then, when your data is in there, we save it into S3 or MinIO, Azure Blob, some sort of permanent storage. So yeah, that's vector databases. That's Milvus. Do we have questions at the end of this, or?
Yeah, we can definitely get some questions going. There are a few that are coming through in the chat, but it takes probably about like 20 seconds for the stream to come through. And you're good with the screen? I can take it off, sharing your screen?
Yes,
or did you want to give the demo?
Let me do it. Let me do the demo. You see this? Yes.
Okay. Yep, I can. Do you want me to ask a question now or at the end of this? So we'll prompt people to ask their questions now, and by the end of the demo, hopefully it'll be full in the chat.
Yes, that'll work. So I'll just show a quick demo here.
There we go.
So we'll say something like, what can I build with LangChain? I think LangChain is on here. And if you try this at home, I would go to ChatGPT and ask ChatGPT what you can build with LangChain and see what it says. Because it will not tell you this. But this one, tells us, LangChain can help us build a variety of tools with LLMs. We can say like, show me how to use conversation chain in LangChain. And it should show, something about conversation chain, which I think is one of the tools in LangChain. But yes, I suggest that you go try this with a LLM and without like any layer on top of it and just see what happens. Oh, see? Builds out the code, et cetera, et cetera. Yeah, that's pretty much it for my demo here.
There we go. There we go. Dude, sweet. All right. So what made you use Go instead of Rust?
That's a good question. I don't know, actually.
That's not what you're supposed to say in this. Make some shit up. We're hallucinating like ChatGPT, man. Come on.
Like ChatGPT. I hallucinate more than ChatGPT. Wow. Yeah, I really don't know though. I don't know like how popular Rust was back when Milvus was written in like 2017. I think Go was like coming out and it was like a pretty popular language and people were like, oh, this is really performant and
Mm.
also safe. Whereas, Rust is actually pretty good for a lot of ML type stuff. I would say that, well, Rust was around in 2016, 2017. Yeah, I know that actually. I'm not really sure though.
All right, well, we got a few more that came through here. How does Milvus compare to Vespa and Quadrant?
How does Milvus compare to Vespa and Quadrant? Well, actually, I have something for you for this.
There we go.
There's this thing called, we just released this thing called Vector DB Bench. And is there somewhere for me to like paste this link?
Yep, just throw it in the chat right here and I'll put it into the big chat. There we go. That is awesome. I think people are going to love it.
Yes, this is a vector database benchmarking tool that includes Milvus, Zilliz, Quadrant, and Weaviate.
Nice.
And with the results for these four, and actually Elasticsearch with results for these 5, and then it allows you to perform your own benchmarking as well. But if you download it, you can see all of the results for these 5 existing ones. And I will just tell you that Milvus really outperforms Quadrant when it comes to load testing, like the number of vectors you can put in there. And
there's spoiler alert. Hold on. Wait for it.
And also queries per second, and for vectors at large sizes and small sizes.
All right, so, I like it. We got a question coming through with Mateo. Okay, how can you cache semantically identical questions that are worded differently? Oh, great question. I like that.
Ooh, that is a really good question. You would save them with the vector, with their vector representation, and if the vector representation is close enough, we'll just return the closer one. It's just straight up just look at the vector representation. No other real tricks there.
Nice. All right. So for more people, so a few people are saying in the chat that they really appreciate your honesty and they love the talk. It was very helpful. And dude, I'm going to direct you over to the chat for people that are asking more questions. Feel free to keep it going. And we just recorded a podcast episode that is going to drop real soon. Hopefully next week, if I can get everything, my ducks in a row, as they say. So I look forward to that happening. And Brady just asked another question in the chat. So I'm going to kick you off, go over there, because I've got a fireside chat to get to, and I'm going to bring on the next guest. As I mentioned earlier, and I will mention it again, you can call me Ringo today, because I'm just keeping time like a clock, baby. I'll see you later, dude. It was great having you.
All right, cool. See you later, Demetrius.
Yeah.